My name is Lei Zhang, and I want to thank Rad Amigos for organizing this and also for the invitation to give a talk. I put the title here as State-of-the-Art Systems Modeling for Personalized Smart Mobility and Demand Management. So I am a modeler. That's sort of my role, I think, in this smart mobility demand management domain. I want to talk about some of the recent developments on some very interesting modeling tools I think businesses and agencies may want to consider using to support the computing or modeling engine behind their demand management and smart mobility or mobility as a service endeavors. I want to start by maybe just a quick look at a history of the two kinds of models I'm talking about here, right? One is simulation modeling. We're simulating and modeling vehicles, multi-model vehicles. We're modeling traffic, right? We're modeling congestion. I know I don't have time to go into the details, and to be honest, after a 2.5-hour lecture I just gave to my graduate students, I'd rather keep this part short. But I want to focus on the last row here, just to show and the kind of interesting new trends we're seeing here. Number one point I want to make here is that model innovations are almost always driven by application needs and by bigger trends in society. And now, when we talk about traffic modeling, we see a lot of applications of parallel GPU cloud computing to support performance-based decision-making. In terms of applications, we're looking at different kinds of demand management and real-time decision support that we need to make that decision, even what traffic management or demand management decisions in real time. These models are getting increasingly faster, multi-resolution, so we can possibly simulate an entire urban area or multiple urban areas in a mega region to be able to be fast enough for supporting real-time application and be able to support and simulate some of the newer vehicles, whether it's connected vehicles and shared mobility vehicles in the system as well. Another type of model that I want to talk about here today is models of travel behavior, which probably has direct relevance to demand management. We're trying to really estimate how people travel, when they travel, at individual level. Right? So we see now, again, the last row here, a lot of integrated planning and operations applications, transportation system management and operations, shared, connected, and automated mobility, and mobility as a service, as new application needs. Then we're also seeing some more and more models there where we actually try to understand and simulate travel decisions and traffic system dynamics evolution at the same time. More descriptive models, because the purpose of these demand management and smart mobility decision is to get people to choose travel choices that are good for themselves, but also very good for the system as a whole. And again, a lot of more computing applications in this domain to make these models faster enough for day-to-day operations of demand management systems. A lot of data to support different kinds of models. Many of you know, but probably not everybody, that Maryland, we have the largest transportation data center and a data analytics center in the U.S. Right now, we archive about 8 billion data records every single day, right? So there's demand-side data, supply-side data about speed, travel time, accidents, parking, weather, traffic signal, special vehicles, transit. And in about a year and a half, we estimate we will archive 10 trillion data records every single day because of the increase in connected vehicles and other vehicles and services in our system just in this time period. So we got a lot of interesting individual level data as well as system level data to support this kind of models, which can then be used for demand management and different kinds of mobility services. The model system right now, when we look at the most advanced travel and traffic model system that could potentially support a great demand management application or mobility as a service application. So these models now are typically characterized by, can people see my cursor on the, or not really? Anyway, it's not essential. On the top right-hand corner of the slides, we usually have these integrated travel models and dynamic models for the entire area where this kind of management is implemented. Then the lower right-hand corner, we take advantage of these models and we can do real-time capable system control and optimization. These are not just control and optimization of traditional traffic control measures or demand control measures. These could be very advanced, personalized signals and optimization of incentives that we use in a larger system. And we can try to optimize them in real time to really make these programs most effective. And these models are supported by the big data I mentioned. They're also enjoying much faster than real-time computing solutions. So you can actually take outputs out of these model systems and make decisions for your demand management and mobility service to deal with real-time demand and real-time situations. And then these models can be applied in a travel interface through smartphones. So these computing models can support different kinds of smartphone apps through APIs and software development kits. They can also support different kinds of agency or private sector client tools, software, and dashboards. Just want to give people a little bit more detail on a typical model system. So in this particular case, this is a model system that we developed at the University of Maryland, and we actually microsimulate on the left-hand side, the pink part of the graph. We microsimulate every single individual, how they make all kinds of travel choices every single day, and also in real time, how they choose mode, how they choose departure time, how they choose routes before they travel, and how they may determine how to divert to avoid congestion or other situations on the road, and how they drive. We can get that kind of real-time data on how people actually drive and try to give them some incentives to change their, improve their driving behavior. And we can do this for every single person in the metropolitan area. Presumably some of them are registered users of a particular mobility service or a particular demand management program. And then we give all that travel demand to the right-hand side of this slide, which are the traffic models. So the traffic models talk to my travel behavior models every 5 seconds. So what this means is if there is a traffic accident, if there is something that happens in real time, it could be a traffic accident that caused a long queue. It could be some other special event. I will have the ability to go back to my demand model, the behavior model, to simulate how everybody will likely respond to that real-time situation and try to optimize demand management or try to optimize different kinds of control signals, whether it's individual level or system level, to be able to manage that event, to be able to manage that particular situation very well. Here I have so here I'm giving one example here is even though we don't have video for this particular presentation, what I want to show is that, for instance, in this case, this is Washington, D.C., Baltimore area. So we actually now can run this entire travel behavior and traffic simulation for every single roadway, every single transit system for which we have data, and also we model shared mobility vehicles in the system as well. We can simulate this entire transportation system, multi-modal transportation system, much, much faster than real time. So what we can do is, now if there's an accident, then we can micro-simulate immediately the impact on every single user in the system. Then we can try to, number one, tell the user about the potential impact on a trip they're making right now or a trip they're about to make later in the day. Number two, if we have a demand management system in place, we could actually start optimizing the different kinds of parameters to really minimize the impact of this congestion. on delay, on emissions, on energy use, or we can start providing incentives to support these different kinds of things, or try to use shared mobility other services to really get a system around this kind of scenario. So that's the first very important feature of these state-of-the-art models, that they are ready for real-time decision support. The second feature is part of the models, so the prediction is not just about predicting how the system will be in terms of congestion, travel time, delay, now and for the rest of the day. For instance, Google Maps uses historical traffic data to infer the travel conditions if you want to reserve, if you want to plan your trip back home after this conference, right? We're actually doing prediction using real-time data and using historical data for more accuracy. But the prediction does not stop at traffic prediction. We also do a lot of travel intent prediction nowadays with a lot of passively collected data from cell phones, from smartphone apps. We're able to do this right now. Historically, when we talk about travel demand modeling, we usually talk about modeling how people will travel 20 years from today. We're looking at long-range decision support, long-range planning decision support. Now, the next generation of travel models does a lot of short-term and real-time travel intent prediction, which I believe is very valuable for demand management, as well as for mobility services, and also for other kinds of revenue streams involving mobile advertising, involving social networking. So what these models does is, based on what we have learned about every single household and individual and the way they travel in the past, at any given time of the day, we can predict with, depending on whether we're optimistic or pessimistic, we can, predict with some level of accuracy of what each person will likely do in terms of activity and travel for the rest of the day. We can predict the destination of the next trip between 62 and 73% accurate. And this accuracy is defined within 200 feet of the actual destination, activity destination. We can estimate and predict the purpose, whether the person will go shopping next, right? Go to restaurant next. This kind of accuracy is actually much, much higher, more than 83%. We can also predict a person's social demographic and economic characteristics when we have tracked a person for more than 30 days. Depending on which particular variable we try to forecast, we get different levels of accuracy. And we can try to predict the activity travel plan for the entire rest of the day for that individual. So this kind of information, when they come together, we can use it for real-time and short-term demand management to provide inputs for different kinds of new mobility service options, to give them the kind of demand information in real time. But of course, others may see value in this for mobile advertising, for giving people coupons just before they need to go shopping, just before they want to go to a restaurant, based on where they want to go for a particular restaurant. So this kind of travel intent prediction, I think, is a new, interesting capability built into these models. I think the third interesting new capability of these models is what I call person-level signal optimization. For many, many years, traffic engineers have been doing a great job, but of course, there are still complaints out there. But I think traffic engineers do a great job optimizing traffic signals at intersections to control traffic for a better system for everyone. But nowadays, we can push this kind of signals at the individual level. It's no longer, so the future of transportation system control or management is probably not all about traffic signals. It's about getting rid of signals that everybody sees the same. It's about introducing person-level signals through individualized, personalized information that we give to the right person at the right time, giving the right person at the right time the right kind of personalized monetary and or non-monetary incentives to get them to make the travel decisions that do not hurt themselves, that benefit them, but at the same time also benefit entire system from a demand management perspective. The control decisions are very different in this kind of modeling environment. We're no longer control signals or decide how much price I charge everybody to use that HOT lane or express toll lane. The decisions we make are, hey, whether or not to incentivize or inform a particular traveler out of the 8 million travelers in the Washington, D.C., Baltimore area, for instance. And if we decide to incentivize a particular traveler, what kind of travel choices we want to influence? Do we want to influence the modal shift? Do we want to influence a departure time change or route change based on our behavior model that predicts how likely this person will change behavior and also the benefit the system can get and the individual can get from that change in behavior? And in order to achieve that, what intensity of personal incentive to actually be delivered to this particular individual? Then the goal is, as I mentioned, it could be system optimality if it's a DOT or agency that's behind this kind of optimization. In any case, no false information to travelers. And if it's a technology, a service provider, transport network company, then the goal may be Pareto optimality among their users. So we want to increase the revenue or make the system better without hurting any single existing user of their service or of their technology. I think these are the three main features I want to highlight. To conclude this brief talk, I want to also offer one example. So this is one application we have developed, our team at the University of Maryland have developed for the Washington, D.C., Baltimore region with U.S. Department of Energy OPRE Transnet funding. Great program. And the goal is to use real-time, personalized information and monetary, non-monetary incentives to do demand management at the individual level. And of course, it's DOE that's funding this. The overall goal is to reduce the total energy use. So we're able to use this kind of model system to help us simulate every single person's travel choices every single day, every single hour, every single minute. So there is a background model here, as I mentioned, that does all kinds of simulation in real time, that does all the optimization given a particular budget on whom to incentivize, who to provide information, then give them monetary and non-monetary incentives to get them to change their travel behavior. And in the end, we're showing that with a $6 million a year budget for the monetary incentive portion of this demand management program, we're able to incentivize about 7.5% of all travelers in this region through individualized real-time or pre-trip incentives and messages, and which will result in about 8.7% reduction in total energy use in the transportation system. If you're interested in congestion, the number is about the same. And well, we did a lot of behavior research to support the behavior modeling on what kind of incentives will work. We systematically explored different kinds of monetary and non-monetary incentives. For instance, we concluded very quickly that just giving people money is not going to work. People feel actually insulted if you just say, hey, let me give you 50 cents so you can change your departure time. Okay, we're going to be kicked out. But we found other things that work, like gamification, simplicity of the message, a point system, very much like a frequent flyer system, making the rewards related to travel and this kind of things, and also get them a social norm and social pressure, social influence is a big influencer factor here also. And we also developed an app to pilot this program in DC, Baltimore. We're doing a limited beta testing in the DC, Baltimore area to make this a demand management platform in this area. But of course, others can use the technology to develop similar apps and models for their area as well. Of course, agencies like to see benefits. I think this is actually good news for all of us who might have interest or businesses in demand management and smart mobility as a service system, because these systems generate statistics every single day, generate performance measures every single day. Agencies can look at these dashboard, which we found to be very important for them. Different kinds of applications, demand congestion management, really providing crowdsourced solutions to a range of smart cities challenges. Certainly a lot of benefits in energy and emissions, and it could also be a good ecosystem platform for smart mobility and mobility as a service systems. That's what I'm talking about, these kind of state-of-the-art travel behavior and traffic simulation tools that, the different kinds of applications of these models, next generation models that are here right now that can potentially support. So that's the talk. We'll be happy to take your comments and questions. Thank you.
Thank you, sir. That was absolutely fantastic. One question, for some of the numbers that you showed, were those estimates or have they been proven in the field, the earlier numbers that you showed?
So that particular energy, 8.7% energy reduction is not based on field test. The field test is going on right now, and that one is based on the model that actually includes every single household in the DC Baltimore area. But the model is estimated based on real world data we collected through tracking. I shouldn't use the word tracking, through behavior research.
Awesome. Well, one thing Ride Amigo is super excited about, we actually have a mutual agreement of understanding in place. We're going to be working together on implementing some of these theories and tests in your research in our programs with Ride Amigo's clients. So we're really excited to work with you this year on that.
Sam here. We look forward to Ride Amigos on our campus this summer. So
yeah, awesome. All right. Well, thank you very much.